Hi everyone. Welcome to this talk on modeling fluid circuits. I'm Ankit, applications engineer at Wolfram, the division responsible for SystemModeler. And today I'm joined by my colleague Sergio, who will be helping me in answering your questions. Uh, in this talk, I've divided this talk into 5 different sections. First, we will look into the applications of fluid circuits, like getting to know why fluid circuits are important. Then I will introduce you to the different libraries that would help you in creating fluid circuits quickly. We'll go through an example, and then I will point you to some learning resources which would help you to learn step by step and create circuits on your own. And finally, we will have some time for Q&A. So fluid circuits are very important, and they're very common in our day-to-day life. You have fluid circuits in your cars. You have the circuit for braking. You have the power steering, and fluid circuits uh, are used in heavy machinery, like in excavators. You use it for the hydraulic actuators. In your office or in your home, we have circuits for ventilation. We have circuits for air conditioning. And we also use fluid circuits in power generation. For instance, in power plants, you have feed water coming in, being converted to steam, and then that steam is used to generate power using organic Rankine cycles and so on. So fluid circuits are really are important, and uh, and you can find them in a lot of application in your day-to-day life. In this talk, we'll be using our tool called SystemModeler. So SystemModeler is a graphical tool which is used for modeling and simulation of several physical systems. So you can model and simulate things which are dynamic in nature, that is things that change with time. So SystemModeler has a modeling interface. You can see the image here, where you have a modeling canvas and you have a huge set of libraries using which you can just drag and drop and create different models. And once you have a model, then you can simulate your model and plot the different results, or in some cases, you can even animate or visualize or have animations of your models. And then you can test different design parameters using sliders, like lookup tables and such. And also you can do various measurements, create plot expressions, and get insights from your model. So in SystemModeler, there are various ways in which you can model a fluid circuit. So there are 3 different libraries which would help you to model such circuits. One is the hydraulic library. This has icons based on the ISO standard 1219, and it has components for direction control valves, proportional valves, cylinders, different types of filters, tanks, accumulators, and so on. Then we have another library called Fluid Heat Flow. This is a library if you are interested in quickly creating a design where you want to analyze heat transfer. So where you want to combine fluid flow along with heat transfer, then you can use the Fluid Heat Flow library. And then there is another library called Fluid Library. In this talk, I'll be using this fluid library to create an example. And this library contains different components such as fittings, valves, different machines, where you can provide your pump curves like head curve or flow or flow curves. And why I choose this library is because it has several advantages. Some of the key advantages are this library is acausal. I will get back to what I mean by acausal when I show an example. It basically means there is no directionality. So you don't need to specify inputs or outputs to the components. The input and output are automatically determined based on the flow conditions. Then using this library, you can, along with the flow characteristics, like you can calculate the friction losses, but you can also obtain the thermal behavior in the fluid flow. Like there can be heat transfer across a pipe. So you can have thermal behavior in your fluid circuits. The third is uh, it's uh, it's compatible with other domains. For instance, you can connect a pump, the fluid pump, with an electric circuit. It can be AC, DC circuit, and then you can combine electrical domain with the fluid with your fluid circuit. Of course, you can have different friction losses. So based on the mass flow rate, the Reynolds number is automatically calculated, and based on that, you can have laminar or turbulent flows, and those are automatically calculated, and the friction losses are computed automatically. Also, using this library, you can have different types of mediums. Like for instance, if you want uh, flow of water, or you want flow of ideal gas, or if you have a custom fluid for which you know the different thermodynamic properties, then you can create your custom fluid and you can add it to the fluid circuit. But we will look into these key advantages when in a few minutes when I create a simple example. So now we'll go ahead and create a simple example to get a basic understanding of how to create models. So first, we will create a simple hydraulic circuit where we have a tank and we have a flow coming in from a infinite source at a constant pressure. It passes through a pipe. Then uh, we have a valve to control the flow. So first, we will model a simple hydraulic circuit. After that, we will go ahead and add a coolant system or a heating system to this tank to understand the thermal interaction between different fluid circuits. And finally, we will add a controller so that we create a controlled system. So let's go ahead. Let me go ahead and open up SystemModeler. So this is SystemModeler's modeling interface that I introduced to you before. And here you can see SystemModeler comes with like built-in a library called Modelica, which has different packages or different sub-libraries on different domains, electrical, magnetics, and so on. In this talk, I will use the fluid library. To use the fluid library, we need some basic components. The first component uh, that we need is a systems component. And what it does is it defines the system default. Like for instance, what is the ambient pressure and what is the ambient temperature and the gravitational acceleration. So once we have this system, the next thing is we need a pressure source. So I will have this boundary PT component. Next thing is I would need a pipe. So I have two options of pipe, static and dynamic pipe. Let me go ahead with a static pipe. And the next thing is valves. So when I go for valves, you can see that we have different types of valves. We have valves for incompressible flow, valves with vaporizing flow, valves with compressible flow, and so on. For this exercise, I will use the incompressible uh, flow valve and bring it here. And then to store the liquid, I will have an open tank, and I will place it over here. Right. So once I have all the components, the next thing that I have to do is put in the right parameters for each of this component. So let's say we have a pressure source which is supplying liquid at 2 bar pressure. So I will select this component, and then I will select the corresponding medium. So with this fluid library, you can select from hundreds of different mediums. You can have different ideal gases, different types of air, like air with moisture, without moisture. For our case, I will use a standard water package. So once I define this medium, the next thing I want to do is define a pressure. So as I said, I will go with 2 bar. So I will write 2, and then here I'm asked different, provided with different units. So I will select 2 bar. I can also select a temperature which is being supplied to this tank, and let me take 20 degrees centigrade for now. And then I have to define a port. Like for instance, like this port defines number of inlet or outlet connections that this component can have. And in this component, I want the boundary only to connect with my pipe. So there is only one port that I want. Right. Next is the pipe component. And in the pipe component, similarly, I can select my medium length. Let me have a 5-meter pipe. Diameter, let's take 0.1 meters. And then I can also provide a height difference, like how would the port B on the right hand side and port A on the left hand side, like what is the height difference between those two ends. And for this example, I will just consider a horizontal pipe. So I will put it as 0. Next, for the valve, I will select the standard water package again. And then I can define some nominal operating point for this valve. So I can say that there is a pressure drop of 0.1 bar across this pipe, and I have a nominal flow of, let's say, 1 kg per second flowing through this valve. Right. But you can see that in the valve, I have this blue arrow, which through which I can pass in a signal between 0 to 1, which shows which provides the position of the valve. And to have that source, I will use a component from the blocks library. So I will go to blocks, go to sources, and then I will use a ramp signal. So I will drag this ramp signal over here. And here, let's say there is a small opening of 0.1. And then after, let's say, 2 seconds, I open the valve. So 0.9 second is the height. So initially I had an offset of 0.1 and then 0.9. So total is 1. So the valve is fully open. And for this transition from 0.1 to 0.9, let's say it takes 3 seconds. So now I have defined my ramp. The final component is the tank. So for tank, I will use the same process, define the medium. Let's say I have a 20-meter tank. And then I can define a cross-sectional area of, let's say, 5 square meters. And then number of ports, like how many input and output connection this tank would need. And let me go ahead with 1 because I'm just connecting my tank to the valve. And then I will set this ports data to false. So what this ports data means is, in a tank, you can define the connection, you can define the diameter, the height of the outlet or the inlet port. So let's say, so for this port, you can define at what height in the tank the port is present and what is the diameter of that port. So in this case, I will use the default settings for it. So that's why I have set the use ports data to false. Once I have that, I have all my components ready. The next thing is I should connect all my components. And to do that, I will click on this connection line tool present here. And then I can drag and I can just connect those 2 points. And here you can see for my boundary, I want to connect port 1 with the port of the pipe. Same goes for the valve, and then for the tank, port 1. And then I will connect my ramp to this. So once I have this model, I will just validate it just to verify if I didn't make any mistake along the way. So now it says that my model is balanced and I can go ahead with the simulation. And before simulating, I can go to the experiment setup and set like how long I need the simulation to be. So let's say I want to simulate it for like 60 seconds, for instance. And then I can click OK. And I can play this, I can click this play button over here. And once I click this button, I am brought to this result view that we call Simulation Center. And in this view, as you will see pretty soon, I have access to all the components over here. So in our case, let's say we want to plot what is the level of water in the tank. So I will click on tank and I will click on level. And here you can see how the level of the tank is changing with time. And we can also change the simulation time. Let's say 1 minute was too small, so we want to simulate it for 10 minutes instead. So I can go to the settings, set the time, and then click simulate. And this is how this is how the tank height is changing. There is an interesting behavior we can look if I simulate for long enough. So you can see that after around 40 minutes, the level of the tank does not increase. It gets fixed at particular height, and that is because as the level of water in the tank is increasing, the back pressure from the tank is also increasing. And I can just plot the pressure at the tank. So reports. So this is the pressure at the inlet port of the tank, and you can see that the pressure increases as the amount of liquid in the tank is increasing. And when it is reaching 2 bar, which is equivalent to the amount of pressure of the inlet tank, then the flow stops. And this type of behavior you can easily simulate using this library, right? And also you can also plot the temperature of the liquid in the tank. And to do that, I will go to the tank. I will go to the medium section, which defines the water liquid for this component, and I can plot the temperature. And you can see the temperature is almost constant at 20 degrees centigrade. Right. Right. So this section, our first example on creating a simple hydraulic circuit is now complete. Before I move on, I will just right click and I will pin this experiment so that I can compare this results with the next experiment that I will do. Right. So once I have my hydraulic circuit, you can see that as the amount of liquid in the tank changes, the pressure at the bottom increased, and when the pressure was equal to the boundary pressure, there was no more flow of liquid to the tank. So that was a flow that was a example from more of a flow characteristics. The next thing that I wanted to show was how can there be a thermal interaction between two different fluid circuits, right? So to do that, I will just create another circuit, and for that I will use again a boundary component like this. And once I have the boundary component, I will use a pipe. This time I will use a dynamic pipe instead. And once I have this pipe, okay, let me do this thing. I will use this as a sink. And then to supply liquid, I will use a, if I go to the sources, I will use a mass flow source this time. So here what I'm doing is in this, using these three components, there is a mass flow source, and this mass flow source is passing through the pipe and going to a tank or sink. So sink is, it has infinite storage capacity. So I'm not using a tank which has a limited storage capacity. So now once I have the three components, let me go ahead and set the parameter for each of them. So here I will again use the same water for this fluid circuit, but it will be at an elevated temperature. So once I define the water here, the next thing is what is the mass flow rate? Let us take as 1. The number of ports I will set to 1 because it's connected to only the pipe component. And then I can provide it a temperature. Let's say water is flowing at 80 degree centigrade, right? Then for the pipe, I can select the same water package. Let's say the length is 10 meters and the diameter is 0.1 meters, right? Yes. But I will do one more thing with the pipe component. What I want to do in this case is to get the heat, to enable heat transfer between the pipe and the tank. And to do that, I will go to assumptions, and then I will say use heat transfer goes to true. And as soon as this goes to true, you could see the red icon appearing on the pipe. That means that through using this icon, I can extract the thermal properties from this pipe, and then I can define a heat transfer uh, uh, value to this pipe, and here I will say constant heat transfer coefficient. If I right click and go to edit, it says it's a type of it's a heat transfer, constant heat transfer, flow heat transfer class. And if I just copy it and bring it here, so here I am just extending this component, which has a parameter called alpha 0, which defines the heat transfer coefficient. So once I have this, the heat transfer property here, I can define the value of that parameter. So I can say alpha 0 equal to 10 watt per meter square and such. So here I can have the parameter name for that flow characteristics, right? And then for the boundary, let me go ahead and keep it as water. And then for this, let's say the sink temperature is at 40 degrees centigrade and number of ports is 1, right? And then I can go ahead and connect this circuit, right? So now I have a heat sink heat component in this pipe, but I would need similar heat component in the tank component as well. So I will click on tank, again go to assumptions and click use heat transfer goes to true, and I will just flip it. Now it has the corresponding heat transfer interface, and then I can just go ahead and click and connect the tank with the pipe. Before simulating, I will just validate to just see if I did things correctly and didn't miss anything. Right, so it says my model is globally balanced. Now I can go ahead and simulate this model and see how it differs with our original model. Right, so now this model is simulated, and here I have my previous plot. What I want to do, I will just remove these two plots for now. So this is the tank temperature for in the first case. In the second case, I will again go to the tank and then go to medium and plot the temperature again. And as you can see, it's simulated up to here. That's because I didn't change my stop time. So to match with it, the first time I had 100 minutes. So for the second simulation, let me also change the simulation to 100 minutes and simulate again. Yeah. And as you can see, in the first case, the temperature was around 20 degrees. And in the second case, since there is heat being added to the tank via the second fluid circuit, hence the temperature, is changing. So there is a flow of heat uh, from the from the secondary, or from the new fluid circuit to the original circuit that we had. Right. So far we saw how to model a hydraulic circuit. We saw how to combine two hydraulic circuit and see how the heat transfer takes place between them. The next thing is let's go ahead and create a controller so that we can control the temperature of the liquid present in the tank. And to do that, I will use a PID component. So if I just type lim PID, it basically stands for limiter PID. And then I have my PID component over here. So this component needs two signals. One is the input measurements, and one is what is the reference that this PID needs to follow. So for the reference, I will just take the original ramp block. So here, let's say my original temperature was 293. So I will use Kelvin for this purpose. So let's say the initial temperature was 20 degrees centigrade, so which is equivalent to 293 Kelvin. And after, let's say, 60 seconds, I increase the temperature by, let's say, 5 degrees centigrade to 302 Kelvin. And this increase, let's say, takes 3 seconds. So this is my reference. I provide the PID with the reference. And then I have to provide the temperature of the tank. I cannot simply just connect a heat port with a real signal. And to do that, I will use a thermal sensor instead. So I will go to the thermal library, the heat transfer, and then I will go to the sources. No, not the sources, the sensors. And then I will use a temperature sensor from that library. Once I have that, then I can connect the heat port from my tank to this sensor. And here I can extract the temperature reading of my tank. And then I can feed it to my PID. And then I can send the output from my PID to control my secondary coolant circuit. So in this coolant circuit, I can control either the mass flow rate or the temperature that is going inside, temperature of fluid moving inside this circuit. Let's say we want to change the temperature inside this circuit based on the control signal. So I will set use t into true, and here you can see I can get, I have this input signal which sets the temperature, and I will connect it to my PID element over here. Now for my PID, if I go in, so here I will keep the default PID parameters, but here I can set what is the maximum value and the minimum value of my control input that is being sent to the circuit. So I don't want to boil the liquid in the secondary circuit. So for that, I will set my Y max to, let's say, 380 Kelvin, 273, yeah, 380 Kelvin. And then Y minimum is like, let's say, 280 Kelvin, so it doesn't freeze. Right. So the output of my PID will vary between this two range, and then I'm feeding it to my secondary circuit. Yet again, let me just validate my result and see how, if things works fine. Yes, and my model is globally balanced, so I can go ahead and simulate the results. Let's hope the parameters were good enough to control the tank. Right. So now, as you can see, my simulation is stuck, maybe because it reached some kind of it's ill conditioned for some parameter value, so it's kind of stopped. So I will just try to see if I can fix it quickly by changing some of the parameters. So since this is the first iteration, some of the parameters, this PID may not be good enough to control the temperature. So let's say I increase the conductivity, and let's say I increase the number of identical parallel flow devices to 100. So this would increase the heat transfer value to the tank, and hopefully that should solve my problem. So when you design a controller, it's a lot of trial and error, where you have to see that you get the right right values in place. So if I simulate for a longer time, so you can see that I'm able to set. So this is the temperature of the tank. It's going at 100 degrees centigrade. Let's see. Okay, so here I made a mistake. So here for the ramp, I had the initial temperature at 293 Kelvin, but the height was 302. But the height should have been 5. So that means that my controlled temperature that I want is 293 plus 5 is 298 Kelvin, or let's say to keep it at 10. So it should be 303 Kelvin. And let me simulate again. Right. Let's see what it right. Yes. Right. Okay. So now again, I think I've reached some kind of I've reached some kind of ill-conditioned state here, because of which the PID is not able to control it, or I'm reaching some kind of singularity at this position. And then to fix it, I need to tune in some of the parameters so that it matches the real world system. But the idea behind this example was once you have these two different systems, you can get the sensor output, uh, for example, the temperature of a tank, and then use it to control the different parameters of a secondary circuit. Like you can control the temperature or mass flow rate in the secondary circuit and control the temperature in this tank. But unfortunately, it didn't work in my case. But anyways, let's move on. Right. So far you saw how we can create a hydraulic circuit, how we can model heat transfer between two circuits, and then how we can add a controller and try to control the temperature of a tank. So using this, so now I will. So the example that I showed was a very simple example, but I want to show 2 or 3 industrial examples or more advanced examples that would show the usefulness of this library. So you can use this library to model complex piping networks. For instance, here I have a piping network where I'm adding heat to one of the pipes, and then I have 3 different valves through which I'm switching the flow across the different pipe segments. And then I can analyze how would the heat addition at one pipe affect the final temperature at pipe 11, or how would the flow change. So as you can see, here is the temperature of the pipe passing through the pipe 8 to which heat was supplied. And you can see that at one instant, there was a localization of heat because of which the temperature increased. And then here, and at the end of this pipe section, that is pipe 11, how the temperature changed. So you can see how the local and the global and how the temperature changes at different sections of your pipe. And this might be important because in a pipe, if there is a local increase in temperature at one point, it might lead to cavitation and other phenomena. So through this, you can model such local heat increase or local temperature increase. And also one of the other interesting things you can see is here for pipe 8, we have the orange curve over here. You can see that initially it was above 0, and after some time, maybe we have opened a different valve and the flow changes. So the direction of the flow through this pipe is automatically determined depending on the flow conditions, depending on the different pressures in the system. And it is automatically derived by the model, and you don't need to define the input and output. So this is what I meant by acausal nature. So the direction is determined automatically based on the flow conditions, and you don't need to define it. Similarly, you can use the fluid library, let's say to model ventilation system. And by that, I mean, let's say you have a room and you have a fresh air that is being supplied to a room, and the fresh air and the stale air is moved out. You can model how if the number of people in the room is being added, so how the carbon dioxide level inside the room would change. And then you can monitor the flow of air through this room and control the total carbon dioxide level in this room. And in this process, you are actually mixing a fresh air with a carbon dioxide gas. So you're mixing 2 different gases and you're passing it to a room. So this shows that you can model mixture of gases flowing to a controlled volume. And once you simulate it, you can see that as a number of people. So this plot shows the amount of carbon dioxide that is being added to a room. And during this working condition, let's say this is an office, and during the working condition, when the number of people increases, the amount of carbon dioxide entering the room increases, and our control system detects it, and then it increases the mass flow rate of fresh air when there are people in the room, and it tries to keep the carbon dioxide at a fixed ppm through the entire day. So here we have model mixture of gases, and then we are monitoring the mass flow rate of fresh air entering the room based on the ppm levels inside the room. Also, you can use the fluid library to model phase change. So in this example, we will see that how you can use model a drum boiler. So what is happening in this example is we are sending in liquid to a boiler, adding heat, and that liquid or feed water is being converted to steam, and that steam is then passed to a sink when the valve is open. And if I see the simulation results, you can see as I pass in the heat, the amount of steam increases, but then I've turned on the valve, and then the steam goes out and the amount of water remains same. And after a certain time, when we have a stable heat input and then we have a stable outlet of steam, so my controller is trying to set of like the amount of volume of water in the tank to 67 meter cube, and then we are reaching a steady state. So the amount of feed water that is coming in, that is converted to steam and it's going out. So this example shows that you can model phase change. So you can have a water and you can pass it to a component, and then you can have heated liquid and steam out of it. So those kind of models can also be simulated. Right. Similarly, this library has been used to model other advanced fluid circuits. It has been used to model refrigeration circuits, and it has been used to model thermal energy storages, which uses molten salt to store thermal energy. And if you want to learn more about this library, or you want to have a step-by-step instruction on how to get started with this library, then we have a 5-part series on getting started with the Modelica Fluid library, which has 5 different examples on modeling a tank, pipe, pump, valve, and pipe heating. So it covers all the basic components, and each of this notebooks has a step-by-step process of how to add parameters and then how to validate the results that you get out of it. So if you want to get started with this library, you can refer to this this 5-part community post, and that would help you in getting started with this, getting started quickly. Also, there are various examples on our web page, which would help you in finding templates that you can use and build your examples upon it. So we have examples on the drum boiler. Also, there are examples on how the pressure inside a tank causes stresses in the outside in the container containing it. And also, as I showed you before, we have the example on controlling the air quality inside the room. So you can use these examples as templates when you are learning or when you're trying to model something on your own. Also, there are various third-party libraries called IBPSA, Virtual FCS, and Buildings. I just wanted to let you know which have used the Fluid library as the base library, and they have created more advanced components like chillers, different types of condensers, heat exchangers, and so on, that you can also use it as a reference to create your own components. Right. I think with that, I have covered what I intended for this talk, and let's see if we have any questions.
Right. So I think one of the viewers is particularly interested into real-time simulation. I'm not sure if you have at hand a quick example just showing that.
Right. I don't have a quick example, but let's see if I can. I think the best place for that would be our library store. So if you go to our web page, we have the library store over here. And here um, you can use the OPCUA. Okay, so there are two things. So by real time, sorry, Sergio, I think I misunderstood your question. So there are two ways. First is we have libraries, OPC, like OPC UA and OPC Classic, which use the OPC standard to communicate with real world sensors. So once you have your model, you can use this communication libraries to have model in the loop or controller in the loop. And that uses, of course, real-time simulation. Also, uh, you can, okay, if let's say, okay, Sergio, let me just quickly create one example then.
No problem.
So I will just create a test example, and then I will drop it here. So I'm doing it live. Hopefully it works. Okay, and then I will switch off my heat transfer for this. Okay, so here and then I can add a temperature input connected to this. So I have my temperature, I have a source, I have a pipe element, and then I have a boundary element like this. Let me validate it first. So what I'm trying to do is I've created, okay, it's balanced. So I have this input connector T in, and what I can do in Simulation Center or in the result view is I can attach a slider to this input, and then I can change this value in real time and see how the output would change. So the next step would be I will go to experiment setup and set synchronize with real time to true. And let's say interval length of 0.1, and I will simulate till infinity. And I will click simulate. Right. Okay. Hopefully that, let's see if it would work or not. And I can add, I can attach a panel, and to this I can attach T in slider, which varies from 283 to 293.83. Right. And then I can plot, what can I plot? The pipe, let's say medium, plot the temperature. Hopefully if I change this, so as I'm changing this, you can see the temperature of the liquid flowing through the pipe is changing. And this input I'm able to set in real time. Right. So there are two things. Like one, you can connect your models with real-time sensors and model it in real time. Second, when you're trying to just trying to simulate things and not connect to different sensors, you can create inputs, attach sliders to inputs, and then simulate it in real time, and then change parameters and see how things change. I hope that answers the question, Sergio.
Yeah, no, that is very nice. Yeah. The same viewer is interested in looking at this, like a next quick show of the C code that we generate in the models. So if you could just like open, if you could just show the C code real quick for one of these. So if you go to
Right.
tools,
Yes, this
sorry,
might be a bit
sorry, in
advanced.
view. Yes, view.
Yes,
Right.
yes. And then where was it? Generated source code.
Yeah. Right.
Yes.
Right. So then you can just go to any of those, maybe. Right.
Yeah, but this is too advanced.
Right. No, no, it's just that
Yes.
one of the viewers was particularly interested into this.
Yeah. So the way of, yeah, of course. So the way is go to view, generated source code, and then you can access the different C files that we generate for this.
Mhm.
Right.
Right. Um, right. I guess what else
Yes.
do we have there?
Right. Okay. And okay, just before I conclude, I just wanted to tell you that apart from the fluid library that I covered, we also have this fluid heat flow library that I quickly covered. And this library is a simpler version of the fluid library. So this is important if you want to quickly test designs just for the thermal, like if you want to quickly test a coolant circuit or such, then you can use this this library. The disadvantage or the limitation of this library is the properties, the media properties like density and viscosity and all. They don't change with temperature, so they are fixed, they're constant, uh, and the friction losses are not present uh, for the pipe element, which is present in the fluid library. So yeah, so this library is also there if you are interested in creating something much more simpler. Or we have this. Let me open it up. Um, yes, so we have this hydraulics library, which is also freely available. And if you are used to the ISO 1219 standard components, then you can use this library. And this has the different the direction control valves, cylinder, pressure relief valves, and so on. And the same limitations are here as well, that the the fluid properties, density and all, they don't change with temperature. And in this library, there is no thermal interaction. So if you want to, for your use case, if thermal interaction is important, then this library does not have that. This is more on if you want to understand the fluid, the conversion of fluid flow to mechanical power. So those kind of interaction, this library is well suited for.
Right.
Right.
Yeah, yeah, and as how you have mentioned, the functionality also has the power to handle phase transitions, which is really, really interesting. Really nice.
Yes. 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 Uh, yes. And as I said, we have this nice community post on Fluid Library, which goes through different aspects step by step, and the different examples that would enable users to quickly get started with this library.
Mm.
Right. So are there any other questions, Sergio?
I don't see anything in particular.
Right. Of course, if there are any questions, you can drop those questions in comments, or you can mail us, and we will, or you can post your questions in the community, Wolfram community, and then we will be happy to respond to them even after this talk. Okay, so with that, I would like to thank all of you for your time for attending this talk, and I hope that that the Fluid Library will help you in quickly modeling the fluid circuits that you're interested in. Thank you.
Thank you.